All right, it's 5 p.m. I'm in a new location, but thankfully we are just swimming with extra monitors in lab. So I'm sharing the PDF of the homework, but I can still see everyone and the chat window. So would someone like to start us off with a question? Oh, and I'm sorry about that doorbell in the background. There's no way for me to turn that off on my phone, which I'm using as document camera.
All right, I got one. I got stuck on let's see, I got stuck on 824 and 825.
Both of those sound familiar. Okay.
Yeah, I've come to the problem session. Sorry if you guys already did them in that, but I'd like to struggle with it until I just can't do it. And
So let's start with 824. And Brian, would it be possible for you to share the information that you did get so far? And then we'll go off of that.
Okay. Yeah, this one, man, it really gave me a tough time. Okay, let's take a look. Yeah, part of it that was getting me. See, I haven't looked at this in a sec because I see a methyl that splits for a doublet, and then those two peaks around 1.8 and 2 looks like they're one each, and then the other two patterns over there are a total of 3. And I see that I have, according to the carbon, I've got a methyl, I've got 2 methylenes, I've got a CH, and then I've got 2 just like quaternary or whatever carbons at the far end there downfield. And then also you've got that carboxylic acid. You can tell from the IR, and you can tell from that far downfield proton in the NMR. And you got the carbonyl with the carboxylic acid. And one of those ones I just couldn't put it together with the mass too. You know, you're just trying to get all the pieces together, and the mass, I couldn't even get the molecular formula on this one. Honestly, it was killing me.
So I agree with everything you've said so far. Thank you so much for sharing. There's a couple things I want to hit up, and the first is a clarification from James. This integral is scaled correctly with these other integrals, correct? So this is reflective of, this looks about twice the height of each of these to me. Is that right?
Okay. Yeah, I guess I can measure it if you want me to.
I was asking James. I'm not sure if that was clear.
Yeah, sorry. Yeah. When I put my grid on it, I get that it's about 0.5 inches, and when I put my grid on the others, I get about 0.3. And it doesn't surprise me. I mean, that one at that position now, I don't know if I'm spoiling anything by saying carboxylic acid, but it doesn't surprise me that a carboxylic acid's integrating a little low. So everything else is integrating about, it's about 0.3 inches, a little over 0.3 inches, about 0.33 inches per hydrogen. And those are integrating kind of at 1.6 hydrogens, doesn't surprise me.
So really quick, anyone who doesn't have one of these transparency sheets already, I put them under the welcome mat at my apartment. So even if I am not around, you can still come pick them up. And if you need to email me, I'll give you the address. So the other thing I want to point out is, of the 2 quaternary carbons, what are their chemical shifts? What does that tell us about the identity of the quaternary carbons? Anyway.
Oh, I shouldn't have said quaternary necessarily, just no proton attached. So they're like carbonyl sort of things.
So I agree with you. When I mean quaternary, I also mean heteroatoms. But maybe, James, am I using a colloquialism, or is it correct?
Yeah, I mean,
those?
I call them quats. I mean, yeah, it's not tetrahedral, but it's four substituents that are non-hydrogen. Yeah.
Okay.
I guess, okay. If I were talking a total synthesis of a natural product, I wouldn't describe them as a quat carbon. If I was talking about depth, I would guess I would refer to them as a quat carbon. But anyway, I think we're all on the same page here.
Can someone explain why the chemical ionization spectra is also provided for us? Because once we have the molecular formula down, we can start moving on the other spectra.
I take it that you don't get the molecular ion in the EI.
Right. And my best guess as to why that is severe fragmentation in the EI mass spec. You just don't see the molecular ion. If the chemical ionization molecular ion is 147, what is the molecular weight of our molecule?
So with that, do I have to subtract like a methyl group that was added on there? Is that how that works? Confused on that.
Not a methyl group, but a proton. So when it says reagent gas methane, methane is just the vector by which you are adding a proton and a charge, because remember in a lecture we drew CH5 plus, only exists in the gas phase and only transiently, long enough to lop a proton onto whatever our molecule is. So it's only +1. The other masses could either be from coming from the gas or from other fragments that are formed by fragmentation. But the important one is this lowest peak in the chemical ionization mass spectra is equivalent to M+1 with a charge, which means our mass that we're looking for is 146. And knowing that, does anyone have a molecular formula and a degrees of unsaturation for 146?
I said it was C6H10O4. I think that comes out to 2 degrees of unsaturation.
Yep, I had to count up because I have the picture but not the formula. But yes, I agree with that. So that was C6H10O4, you said? 2 degrees of unsaturation. Where are the 2 degrees of unsaturation coming from?
2 carboxylic acids.
And why do you say that rather than a carboxylic acid and a ring or some other pattern?
Just by looking at the integrals of the carboxylic acid peak, it looked like you mentioned something about it being scaled correctly, and it looked like it was approximately 2 protons, because it was more than 1 but less than 3. So I just kind of I made the assumption that it was 2.
I would agree with that. So James, correct me if anything I say is incorrect, but due to rapid exchange, carboxylic acid proton peaks are broad and occasionally integrate for slightly less than what they should. So if this is meant to be 1, it might appear as 0.9 or lower. If it's meant to be 2, it might appear as 1.8 or lower. And in my opinion, that's what we observe. Again, I wish I could put the ruler up to my screen so that you guys could see it. But this looks like relative to, and we determined that this was a methyl doublet, relative to the 3 protons of the methyl doublet, this looks like 2 protons to me. So those carboxylic acids, we can tell that the carbons aren't coincident because we see 2 distinct carbonyl carbons in the carbon NMR, but the carboxylic acids, at least to our eyes, appear coincident in the proton spectrum. Knowing that, what other fragments can we put together? So 2 carboxylic acids is a great start, especially since we know they're different. So it's not symmetric.
It looks like that methyl it only couples with one other proton. So you've got like that, what is it called? Like a methine when you just got a CH adjacent to the methyl.
Yes. So does everyone understand that explanation? Because the 3 protons of the methyl are a doublet, it's adjacent to a carbon that only has one other proton on it. So it has to have 2 other substituents, be they a heteroatom or another carbon. You're only having the 1 proton's worth of coupling. So I could draw this out, or we could just keep going and continue building out the fragment. Let's see what else is there. So since we know that the methyl is coupling to a methine, maybe we can take a strategy that we took in lecture today and find its coupling partner. So where does the methine show up on this spectrum?
Maybe around the 2.55 signal.
And why do you say that?
It's the thing that looks closest to a quartet. Maybe. But then I guess it needs to be next to other CH2s, so never mind.
Well, not necessarily, never mind. Why do you say it needs to be next to other CH2s?
Well, I know that there's 2 different CH2s based on the CNMR.
Right.
And they need to fit in somewhere, so.
So this is our first discussion where we've had depth spectra. And once again, I sent an email, but this middle carbon depth is the C135 spectrum, and signals that point downward indicate that that carbon is a methylene, or it has 2 proton substituents and 2 non-proton substituents on it. So if we have the 2 CH2 groups, well, that's what we've determined based on this depth 135, is that there's 2 methylenes and no other methylenes in this molecule. Let's see, where can we go from here? Well, maybe we have enough to put the fragments together. I'm going to go over to my document camera. So we identified 2 carboxylic acids, but they're not necessarily equivalent to one another because of the, they show up differently in the carbon NMR. We know that there was a methyl group adjacent to a methine, but at the time we didn't necessarily know what the other substituents were. And then we know that we have 2 other CH2s based on the depth 135. Can someone help us out with the connectivity of any of these groups? We haven't talked about the chemical shift of the proton spectrum yet, so maybe someone could mention that.
What I would do at this point is I would put my acids on the end. I'd stitch them together with methylene groups, and I know that one of those, I have to stick a methyl on it and turn it into a methine. So it can be alpha to the carboxylic acid, or it can be right in the middle, it can be beta. But I don't think it's going to be, I think it's going to be alpha.
Why do you say that?
I'm thinking it would be pretty symmetrical if it was in the middle. And I wouldn't get, I don't know exactly though, but I think how different the peaks look.
Your intuition is exactly correct. If the methyl were in the middle, we would have a plane of symmetry through the whole molecule. And these 2 carbonyl carbons, which I've drawn the skeleton structure, but these 2 carbons we identify as the 2 quaternary carbons at 180 and 183 ppm in the carbon spectra. If they were symmetric, those would be coincident. And we had a problem on the homework, I believe it was problem 6, some Silverstein problems about different symmetries of diethyl phthalate and how many coincident carbon peaks we would expect in the carbon NMR based on symmetry. Because those 2 are different, we know we can't place it in the center, and therefore it has to be alpha. There's only one of 2 positions, and if we were to flip this over, it would be the same structure. So excellent job, everyone who contributed. Thank you. Do we have any follow-up questions on 8.24?
I have a question. I've been having a hard time kind of just determining what the molecular formula looks like from the mass. Because I mean, I understand the 2-carboxylate acid, but I don't understand maybe the rest of it. Like, how do we find whether the carbon, or sorry, the hydrocarbon chain, whether they can deviate or not?
So, sorry, you're asking about the molecular formula, determining the molecular formula? One second.
Are you using my desk?
Yes. You're asking about the molecular formula?
Yeah. Like, I know how do you find out the 2-carboxylic acid, but then the rest, I'm just kind of like iffy, because then you could also determine if it's like a double bond that's missing or something like that. I'm sorry, I'm a bit lost.
So for the molecular formula, if I could briefly explain my strategy. Am I sharing the right screen? Everyone sees my PDF right now?
Yep.
Okay. My strategy is, first of all, if there's a chemical ionization, subtract 1 so that you have the right number. Second of all, the nitrogen rule says that if we have an odd number, most of the time, if we have an odd number molecular ion peak, then we have an odd number of nitrogens. So factor that in. And then if I see a nitrogen, I'm looking for amines or potentially amides in the IR spectrum. Isotope patterns. So this just looks like a regular. We have a couple of C13s, or a couple, some amount of C13 contributing to that small peak. But if we have a halogen like chlorine or bromine, we'll have a more obvious isotope pattern or even some unusual metal ones. And my strategy is usually jump to the proton NMR, find the smallest one, assume that the smallest one integrates to 1 at first. That's not always correct. Sometimes it's 2, but or there's symmetry, and so it's some other number. Add up all of the integrals. So this would be 2 plus this is 3, 5, 6, 7, 8, 9, 10, which that ended up being H10. So this ends up being correct. That is the number of protons. What I do is I take the molecular ion number, I subtract the number of protons, and I just divide by 12 for carbons. And if it divides evenly, I figure out whether I have a reasonable number of degrees of unsaturation and go from there, because it means that it's just a hydrocarbon. If it doesn't divide evenly, that means that it's not just carbons plus protons in the molecule. There could be oxygen or nitrogen. And that is when the IR is most useful, because oxygen-containing functional groups are usually pretty obvious in IR. So once I've determined whether there's 1 or 2 oxygens, factor those into the molecular formula. So take the molecular ion peak, subtract the protons, subtract however many oxygens I think I have, then divide by 12. And if it divides evenly, I figured out the number of carbons. That's my strategy. Other people could use different ones, but for the time being, does that answer your question, or do you have follow-up questions?
I guess that answered a little bit of my question. I think I'm just having a hard time putting it in practice. I'll just figure that out on my own time.
Everyone will have lots of opportunities to determine very complicated molecular formulas from Silverstein problems. We have lots to look forward to, and I will help. Any other follow-up questions on 8.24 before we jump to 8.25?
Yes, I have a couple of follow-up comments. One of these is in the CI mass spec. You notice we have little peaks at M plus 29 and M plus 41. And those are straight out of Silverstein when they talk about CI mass spec and seeing adducts in CI mass spec with methane, seeing adducts with ethyl cations at M plus 29, and with allyl cations at M plus 41. So that's one thing that I thought was quite literally textbook there. The other one is just a hint that I'd urge people to get that buzz in their eye or ear. And if you can scroll down to the proton NMR spectrum, seeing those two peaks at 1.8 and 2.0 ppm, the multiplets, one of them running from, I guess, 1.66 to about 1.89, and one running from about 1.96 to about 2.08. Seeing those, seeing how they look like they go together, they're tenting inwards, they're one hydrogen apiece, they're separated by a couple of tenths of a ppm. To me, that pair just screamed stereocenter, or at least whispered it in my ear really strongly. And so I was thinking that that was a methylene next to a stereocenter. Might be something else, but it sure was looking like that to me. So that was one other tool I used when I read this spectrum, in addition to recognizing that there was a methyl group next to a methine.
Thanks, James. So 8.25, I spent a long time on this in the jam session yesterday, and I feel like the explanations I was giving weren't particularly useful. This is a very unique problem. There's a lot of non-traditional stuff going on. James, would it be all right if I tossed this one directly to you so that you could find the useful information out of it, and then we could move on to a different problem?
Yeah, so this one doesn't draw upon our, what I'll say, traditional skills of reading a problem. In the sense that the proton spectrum isn't very readable, the carbon spectrum isn't very readable. What I got out of those was basically some questions of symmetry. And so I got out of it that there were 3 types of carbons. I got out of it that there were 3 types of hydrogens in there. I got out of it that from the depth spectrum that there was a methylene group as well as a couple of methine groups. I got out that there seemed to be something that looked like an olefin. And from the mass spec, I was pretty sure the formula was C7H7. And the coupling pattern didn't talk to me one little iota, confused the hell out of me. IR spectrum didn't look like a carbonyl compound, which ends up being consistent with the formula. It does look like there's some sort of vinyl compound. There was something weird going on with the shift of the CC double bond stretch. At that point, it was pretty hard. And one of the ways you could approach a problem like this, and we'll throw out a couple of problems that are high symmetry problems. I think it's a really good skill set to be able to come down and say, this isn't talking to me. I know I've got some high level of symmetry. What in blazes could fit a highly symmetrical formula with C7H7? And that's kind of where I was at. Most people will not get this problem. This problem is Norbornadiene. And basically, if you start trying to sketch out isomers of C7, and I said H7, but I meant C7H8. If you start trying to sketch out isomers and figure you've got some olefins and a methylene and 3 types of carbons, you might be able to get it. Chances are not. In terms of what's going on, so James, why don't you draw in, or I guess you've got can people see my screen here, my whiteboard, if I write really, really, really big?
Yep.
All right. So Norbornadiene, if I were a really good person, I would be able to do that drawing and anticipate where the bond crossed. Norbornadiene is about as non-first order as you can get. even if everything's very separated, I guess we would call it A prime, A double prime, A triple prime, M prime, X prime as a spin system. And it is really hard to apply any sort of first order analysis. I told you, you can't really get away with it often. You've got virtual coupling going on, or to put it another way, things just are broken down. Furthermore, the Norbornadiene, so basically, in other words, this proton here isn't just coupled to these two protons, it's coupled to these two because they're on top of these. Very much like the systems we looked at for tetrahydrofuran and also for glutaric, or I guess it was adipic acid, right? It was, yeah, it was adipic acid that we looked at where things just went to heck. So I can't get too much out of that. And that's a good skill set to have, where you just have a super high symmetry situation and you need to draw upon different skills of thinking. And most people will not get this problem. I'll tell you, I think we included that, James, we included that problem that you created for last midterm in the homework now.
All three of them, yes.
Yeah. So James, I had gotten a student in the Borovic group came to me and they were trying to figure out what was going on with a proton NMR spectrum, a protein NMR spectrum. And it wasn't a protein, it wasn't a peptide. And there were some really unusual peaks and couplings going on. And it was a fun little detective story for me because I had to figure out where this came from. They came to me, it had nothing to do. They said, I never worked with that molecule. I said, well, got in there, and I figured out how it got in there. And it was just so cool that we decided to share it on the midterm exam and then share it. Now you guys are getting it as a problem. But little bits of symmetry and coupling talk to me on that. And so that's a sort of a complementary skill set to have. We'll throw in a few other high symmetry problems to help you think outside the box, but almost nobody ends up coming up with this, and that's okay.
I would like to end. Oh, go ahead. So I'm sorry.
Yeah, like at least like which proton would be what? Can you tell us? I'm just like really curious.
Oh, yeah. Okay. I think pretty easily. All right, my interpretation, obviously the vinyl protons are the ones at 6.7. And you can immediately see this is not your typical isolated double bond. It's not at 5 to 6 ppm. There is some additional orbital overlap going on here that makes it almost like a conjugated system where there's interaction between these two. So this is behaving that way. My take on this was that the methynes are at pretty much a normal position, and we know something weird is going on with that methylene group because in the carbon NMR, it's at 75 parts per million. And you don't expect a methylene group to be at 75. Can you see my screen here? Am I off the board? Let me give my camera a little tilt here. You do not expect that carbon to be at 75 parts per million. And you don't expect these protons of a methylene group to be at 3.5 parts per million. But that's my take on this. My take is that the protons are also way more downfield. And when we talk about pi systems for benzene, we talk about pi systems as having a ring current, and that ring current ends up shifting down the hydrogens of the benzene. I said you can kind of think the same for an alkene, where anything that's right over the benzene would be shifted upfield, would feel a weaker magnetic field. But things that are off on the side, you sort of got your right-hand rule going and your flux lines and your applied B naught, that these protons feel a higher applied magnetic field. And I'm betting the same thing for these protons here, because normally you'd say, oh, methylene group, you said 1.4 ppm. But I'm guessing these guys are shifted downfield to 3.6. I'm guessing this methine is pretty much at the plain vanilla position of 2 parts per million or 2.1 parts per million. The carbon NMR is 50 ppm, which is no huge surprise. So I'm guessing we're really seeing a ring current effect on this methylene. But yeah, this is unusual from all counts here. And this is not such an oddball compound, because I come back to this protein NMR, and okay, most of you are not going to work with proteins, but you are going to work with ligands. And your catalyst drops a ligand into your reaction mixture. Ligand dissociates. Norbornadiene is a common ligand for metals like rhodium. Your catalyst drops a ligand into your reaction mixture, and you see these peaks. You can't make out what they are. That could be your ligand. Remember I talked about dioctyl phthalate and Tygon tubing? Yeah, that's another case. You're not expecting dioctyl phthalate. You're not, and you're certainly not expecting a weird-ass aromatic pattern that doesn't seem to make any sense from that orthosymmetrical disubstituted aromatic. You see that there, and you're thinking, what happened in my reaction? And it's not what happened in your reaction, it's what oozed into your reaction. You see this, now this is way more volatile than dioctyl phthalate. Norbornadiene is going to be volatile, but maybe you're running a reaction in an NMR tube and looking at everything. You see this, you think, what happened to my substrate? And it's not your substrate, it's your ligand from your catalyst. So keep your eyes and your minds open when you use NMR to read what's going on in your chemistry. I'll turn it back over to James and to the various additional questions that we can call out for.
I'd like to end on a hopeful note, which is after the midterm, we'll get into proton-carbon correlation spectroscopy that allows you to build skeletal frameworks, especially of molecules similar to or derived from norborane, because you can see which carbons are bonded to which carbons. If you've never used an HMBC or HMQC spectrum to try and put together a molecule before, it's a totally different experience when you have that information. So it's something to look forward to, and it makes these problems solvable. Were there any follow-up questions on, this was 8.25? Okay. Other questions? No one sent me anything in the chat that I can see. So if someone would like to, anything.
Can you do the next one? I'm kind of stuck because I don't see any functional group or heteroatoms. (8.26).
There are no chlorine.
Another one that has a lot of challenges to it for many people. So you're right with the best of them in finding this challenging.
The only thing I can contribute, Partho, is I see the mass spec So I didn't get this, by the way. I have no idea what we're going for, but
Could
I see in
someone
the.
other than me try speaking to see if I can hear?
Can you hear me, James? Hello, hello, hello. No, no, no.
Sorry, I'm not getting anything. I'm gonna leave the call and come back. I'm sorry.
Is there a chlorine in this compound as possibly suggested by mass spec?
What do
Yeah,
people,
that's,
what do
Okay.
people think?
I'm with you, Chris. Chlorine. And
Yeah, you've got that N-35 peak there
yeah.
at 121.
Mhm.
Hmm.
And there's possibly an aromatic ring as well. Oh, hey, hi, James. We're doing 8.26, and Chris just said that there's a chlorine, and Phil just confirmed it by saying that there's M-35, and I just said that there's an aromatic ring.
I agree with all those things so far. Sorry about that. Thank you for carrying on.
I want to add, I think we have a methylene group that is insulated from any other coupling. Maybe, we'll see. I don't know.
Oh, you're calling it, Brian, that singlet in the proton?
Yeah, it's real de-shielded too, which I came up with. I don't know if it's the right explanation. We'll see. I think it's really de-shielded, but I think it's a methylene.
It's probably de-shielded because it's maybe coupled with chlorine on the other side. Maybe. I don't know.
I had it as like an acetal sort of deal.
Does an acetal agree with the chemical shift of that isolated methylene up all the way to 6?
I don't know.
What would the chemical shift of a methylene that's adjacent to 1 oxygen atom be?
3 or 4, between 3 or 4. So I think that does agree. I would agree with Brian. Maybe, yeah.
Yeah, I'm thinking you got like a 1,2 phenol thing and like a formaldehyde kind of. You add that with some acid.
Yeah, maybe it's like a catechol type system that is protected by formaldehyde.
My document camera also fell victim to whatever technical issues I was having earlier. James, would I be able to call on you to use your board so that we can
Sure.
put some fragments together?
Sure, and I'll write nice and big. So it sounds like right now, what I'm hearing is catechols, orthodisubstituted benzene acetal. Is that where we're at?
Yeah, and I think you
Yep,
got
that sounds good.
chlorine too that we have.
So with the idea that maybe the really unusual position in the proton NMR and even more unusual position in the carbon NMR, 102 ppm for a methylene, so that's just not a methylene next to 1 oxygen, and ditto for your 5.96 ppm, that's not a methylene that would typically be just next to 1 oxygen. And so that could explain it. So that might be something. I also heard from the mass spec that people were thinking chlorine.
So where does the chlorine go?
This one tripped me up too, but I put it so it's a 1, 2, 3 sort of deal. But yeah, these they still give me a tough time.
In the proton NMR, there are two integrals, but more than two signals. And if we have a tri-substituted aromatic ring, that means we have three distinct signals that we should be able to pick apart. What are the three signals? What are the splitting patterns? And what are their coupling constants?
We've got a triplet of doublets and we have a doublet.
Is it a triplet of doublets?
Apparently not.
Sorry, I'm not trying to single you out. Does someone have an alternative explanation?
Doublet of doublet of doublet with maybe.
Let's look at the integrals, because in theory, so if it were a triplet of doublets, we would expect the middle signal to be twice the integral of the two on either side. And if it was a doublet of doublets, we would expect them to all be equal. When I put my transparency paper up to it, it kind of looks to me like that first doublet, the one on the left, accounts for half of the integral of that whole pattern. Would others agree with me? What does that say about the two signals to the right of the one on the left, which is to say the second and the third one?
It's one proton.
One proton. What is that pattern?
Doublet of doublets?
A doublet of doublets. So it doesn't always show up, but it's so cool when it does. In this, and there's one on the homework this week that's like this too. Protons tend towards the protons that they couple to. So you see two different directions in the tenting of that doublet of doublets. The larger J value, the doublet on the right is taller than the one on the left. It is coupling to the doublet at 6.72 ppm. But the smaller J value of each of the small doublets in that middle proton are tented to the left. They're coupling to the tall doublet at 6.82 ppm. So on an aromatic ring, what does a large coupling constant correspond to, and what does a small coupling constant correspond to?
Large is going to be like cis, and then the small is W.
Yeah,
So
so
ortho and meta.
Ortho and meta, to use the terminology of the aromatic ring, right? So if we have a doublet with one small J value, what types of coupling does it have?
Just meta.
Just meta. How about the second proton?
Meta and ortho.
And what about the last one?
Just ortho.
What substitution pattern? So we know we can't pull the oxygens away from one another because they have the bridging methylene. They have to be adjacent. Where can we put the chlorine that satisfies each of those criteria?
Just one over from where James put it.
So relative to the oxygens, it would be 1, 2, 3, the 4 positions. So this would be 1, 2, 4 substituted.
Yeah, and it's only 2 positions that you can even put it in because it's symmetric.
Right. That being the case, which proton, so how would you assign these protons? If from left to right they go A, B, C, how would you assign them?
The most shielded one would be the one ortho to both oxygens, right? Or
Why is that?
because it's if you draw a resonance structure where you have the negative charge on that carbon, so I would think that C would be the one ortho to that carbon.
Can you use an argument other than shielding?
Nope. I'll call a friend.
All right. I think I got it. So the one that is it's a doublet, but it's only a small splitting, that has to be the like isolated one that only has meta coupling. So that has to be the one that's furthest downfield, the one up top. And you can follow the same logic for the other two. The one that's a doublet with the large coupling has to be the one with only ortho coupling. So that's at the bottom.
Which leaves B for in between because it couples to both A and C. Excellently done. I have good news and bad news. The good news is last week we had an unsatisfying aromatic splitting. This week this is very satisfying. You can assign the protons exactly because the ortho and meta couplings are distinct from one another. Coupling is mutual, so you can tell which protons are coupled to which protons. That's the good news. The bad news is this only holds for all carbon benzene rings. And when you throw a heteroatom or you change the number of carbons in the heterocycle, the coupling constants differ. One example would be in a pyridine, you generally don't see metacoupling from the proton adjacent to the nitrogen to the proton on the other side of the nitrogen. That's just one example. But the good news for that is the Prech textbook has all of the coupling constants and shifts for a bunch of different substitutions of pyridine. So if you find yourself coming to the conclusion that you have a heterocycle and you're trying to assign aromatic protons, the Prech textbook is a good resource for that. So I guess it was all good news.
Generally, protons next to a heteroatom have slightly smaller J values.
I have a quick question on the ortho and meta coupling. So I'm looking at Appendix F and it says that orthopara is about 9. It's about 9 hertz, and I'm confused how you know that it's ortho by looking at the peaks.
So you said ortho-para coupling?
Maybe I'm looking at the appendix wrong. It just says it just gives me the hertz for ortho, meta, and para. Am I supposed to be looking somewhere else?
No, that's correct. So
Okay.
sometimes you'll be able to see para coupling of protons across the aromatic ring, but in general, ortho, where they're adjacent, and meta, where there's that would be the 4-bond coupling. Those are the two that are diagnostic. In this case, I'm going to share my screen really quickly. If you look at the proton spectrum, once you've deduced that this signal is distinct from this signal, you see that there is a coupling that is large, which is the same as the distance between these peaks and these peaks. And you deduce that there's a small J value, which is the same as the distance between these, and these. If you know that you're only dealing with 2 coupling constants on an aromatic ring, and one is big and one is small, you can assume that it's ortho and meta. If you get to the stage where you think there might be para coupling on 300 hertz instruments, no, that's not quite right. So sometimes they're resolved. Sometimes you can see them. And there was a problem from last week where there may have been para coupling, but in general, para coupling's not observed, or if it is, the peaks are overlapped so much that the line doesn't go all the way back down to the baseline in between. It looks like there's maybe a tiny little valley at the top, but otherwise the peaks are way squished together. Does that make sense?
Yeah, it makes sense. So when I'm looking at the spectra, I shouldn't rely on the 9 hertz value in the appendix F. I should just look at like the smaller versus the bigger coupling to decide if it's ortho and meta.
If you are given an expansion where the x-axis is given in hertz, or you're given a peak table where you can identify the exact hertz coupling, it is worthwhile to do so. However, because there's only 2 coupling constants and because we're not given an expansion, it is sufficient to make the assumption that the large is ortho and the small is meta.
Okay, thank you. That clears it up.
I got a question to demonstrate the modeling component of this homework, and unfortunately I can't do that with my current setup. I'm kind of on a borrowed technology here, but I can answer questions by email. I could potentially record myself answering a question and then distribute that Zoom recording, but I don't think that with the time we have left that I would be able to answer that question right now in discussion. So email me. I guarantee you other people have the same question, and we can set up a time outside of discussion and I can go over it via Zoom. Are there other questions from this problem set in the time that we have left?
No one else has one. I've got one more. I just don't want to take up all the time today. So if anyone else.
Do it. I'm sure we all have the same question.
Okay.
Yeah, go ahead, Brian.
Well, and I feel like I was right on the edge of getting this one, but I just couldn't quite do it. 8.21. I don't know why this one was getting me.
Aha. All right. No, I'm not muted. All right. Because you said you were very close to the solution, would you mind walking us through the information that you've got so far? Sorry to keep putting you on the spot.
No, all good. All good. I mean, I thought I was close, and I was like, oh, okay, I'll just wrap this one up after. But I had an acetal in there. And now, after we did that previous one with the acetal, looking at the carbon shift, I don't think it's an acetal anymore. So that's it might be way off. I might not even be close now, but I had C8H14O3. Is that so far so good?
How many degrees of unsaturation does that give?
2?
That is correct, yes.
Okay.
I agree.
So that, you know, I got a carbonyl there, and I have what looks to be an isopropyl group. Looking at my methine and my my methyl peaks around 1.9 and 0.9.
I'd like to really quickly emphasize this is absolutely diagnostic. When you see the septet and the doublet, you should immediately be thinking isopropyl group. It's one of the very few things that will let you know exactly what it is in the NMR. So yes, I agree.
Good, good. And then I've got a methyl group, which I think is the alpha carbon of a carbonyl.
Why do you say that?
Because it's a sharp singlet. It splits for 3, and it's about where I would expect it to be based off the de-shielding.
I don't mean to be pedantic, but by split, do you mean integrates?
Oh yeah, my bad. That's right. Exactly.
So you're right. That is an alpha methyl. Yeah, for the reasons you stated.
Cool. And then I've got 2 more that are further downfield that each integrate for 2, one of which is a doublet, one of which is a singlet. And that was what tripped me up here. And that's where I got stuck.
So in terms of fragment thinking, we know that there is a carbonyl, an isopropyl group, and that the carbonyl has an alpha methyl. So we can call it terminal. Again, phone died, document camera not set up, but our fragments are, at least on one side, we have carbonyl with an alpha methyl, other side, isopropyl, because isopropyls by definition have to be terminal. They don't have anything else hanging off them. It looks like James is going to help me out, so I'm going to stop my share so that we can look at his board. Can someone help us out with what could possibly be connecting these two? And maybe I'd like to draw our attention to the chemical shift of some of these protons that we haven't identified yet.
I mean, they're pretty downfield.
Yeah.
I think the singlet with the 2 protons near the 3.4, 3.5 might be located between 2 different carbonyl carbon, which might have explains its singlet ability, while the doublet that has 2 proton might be the one that's right next to that CH, because it's picking up maybe the splitting from the CH. This is my best detective ability has led me to.
Yeah, I'm gonna agree with that. I'm actually gonna argue that septet might be a nonet.
Interesting. So we didn't get an expansion, but why do you say nonet?
Like that's really the only way it kind of like fits. Because if we like, what's really telling me is that like doublet at the end. So based on the chemical shift, I think that's like kind of on. That's that methane or right?
Methine.
That methine is next to an oxygen for an ester based just on the chemical shift. And then it was the only way for me to like think about it and fit all the pieces together.
Another way that you could have arrived at that conclusion is there is a single methine in the carbon spectra. So we identify the methine being part of the isopropyl, but there's more than one doublet in the proton NMR. The doublet at 0.9 are the two methyl groups of the isopropyl, but we have an additional doublet at 3.9 ppm, which indicates that there has to be at least one other set of protons being split into a doublet by that same methine. And you can convince yourself of that because the coupling constant's the same too. So another thing I'd like to point out is, and I'm not sure that this will ever come up again, but the carbonyl in the IR, it does look unusual. It doesn't come to a single point. And my hypothesis is that's an asymmetric, symmetric stretch from the diketone.
One is an ester, one is a ketone.
Yeah, so one's an ester, one's a ketone, right? So we've got, are we all over here at this point where we've got isobutyl acetoacetate? So there might well be some sort of coupling between these, but one of these is a ketone, one of them's an ester. So normally you'd expect them maybe about 20 wave numbers apart. And you kind of see that going on in the IR spectrum where it almost looks like, although only one got picked, it almost looks like in the IR you've got kind of this little thing going on over here where there's maybe a little bit of a split to that. So if 1735-ish is sort of a typical ester, 1705-ish is a typical, 1715 is a typical ketone, I could believe we're seeing two independent carbonyls.
That's more reasonable. You're right. Thank you.
So one thing that caught me when I looked at that peak that we've talked about is the pattern on it. Now, it didn't look quite like a septet to me because a septet, we are seeing 7 lines that I can count there. But a septet, normally, a perfect septet is 1 to 7 to 21 to 35 to 21 to 7 to 1. And we're seeing a little bit more going on there. And a perfect no-net, based on my Pascal's triangle, I think, is 1 to 8 to 28 to 56 to 78 to 56. And what caught me when I looked at it was there's a sort of a spiky little bit at the middle. We see a little nubbin over here, and then a peak, and then a peak, and then something that comes up pretty high. I'm exaggerating it a little bit. And so it caught my eye. And of course, a no-net would depend on everything having exactly the same J value, pretty close, but my eye makes it look like this doublet is a little bit tighter than the doublet for the methyl group. So I don't think our J's are exactly the same. So if you wanted to analyze it, and I wouldn't even try septet, it may be akin to a septet of triplets, but I'm betting that our J's here are about 7 hertz, and with the heteroatom of the oxygen, maybe our J's here are 6 hertz. It looks just a hair smaller. So I wouldn't try to describe this as more than a multiplet, but it doesn't surprise me that it's not just a plain vanilla isopropyl group over here. So yeah, this is the compound. It's it's isobutyl acetoacetate, or 3-ketobutyrate is another name for acetoacetic acid. So that's the compound that you get there.
I'd like to explain a tangential question really quick. So the format of the strychnine NMR data on Canvas, if you go to a folder and actually, sorry, I'm getting ahead of myself. I should have opened this up in a window and then shared my screen because it's much easier to show it that way. So let me really quickly get to Canvas. Oh, they're going to make me use the Duo Pass. No, okay, good. It was within 24 hours. Come on. Okay. So we're in Files. There's a subfolder called Strychnine NMR. This experiment numbers text document is just for each experiment number, there's an experiment associated with it. So right now I've done proton and carbon. As soon as this is done, I'm going to go take the 2 depth and upload them into this folder. This is the strychnine folder, and I've talked to a lot of people on a lot of different operating systems about the best way to get this to open in Topspin, but generally you can copy this exact folder into your Topspin NMR data directory, and Topspin will do the rest. But the contents of this folder are each of the different numbered experiments. 1 is proton, 2 is carbon, 99 is just the proton that I use to shim it each time. I call it 99 because it's at the end, it's convenient to do it that way. And then there are other miscellaneous files inside each of these, notably FID, which if you were using MNOVA, this is the file you would actually want from all of these. But again, I'd like to reiterate, I update this whole folder, strychnine, with each experiment as I take them. So all you need to do is continue dragging and dropping this into your Topspin data directory. Any follow-up questions on how to get this into Topspin? I can answer simple ones now, complex ones by Zoom later. Okay, sorry to interrupt with that tangent, but someone had a question about Topspin. I want to make sure I addressed it. We're at 6:02 now. So that's the end of discussion. But again, I will continue answering questions about this problem set and any problem set and any problem using software related to the course all evening. If you would like to turn in your problem set in person, email me. I'll let you know my address. My wife and I have a welcome mat that's got 3 cute birds on it, and you can leave it right underneath there. I'm sure by the time I get home tonight, it'll be significantly off the ground. And there is an envelope with these transparency sheets underneath the welcome mat. So even if I am not at home, you can pick those up. And really, these are invaluable for this week's homework. I know it's inconvenient because of the COVID times, but if you're able to pick one of these up in person, do so. If not, James and I will make arrangements for you. Any last thoughts before we peace out for the day? All right, sounds good. Thank you all for your time. I hope this was useful. And if you've got follow-up questions, again, email me. I love emails.
Thank you, James, both of you.
Thank you.
James, really quick before you go.
Yes.
So I've just been having a hard time getting it into Topspin. Do I put it in a data file or an exam data file?
It should go into data. Exam data is example data. I don't think that it might work, but that's not the one it needs to go in. Okay. Furthermore, you can replace this same strychnine folder every time. Or one thing that I was actually thinking of in your specific case, because we did Zoom call last week, is rather than messing with the strychnine folder, each new experiment, dragging that into the strychnine folder itself. Does that make sense? So for example, this week, you already have a folder called 1 in your strychnine folder, but you don't have 2. So you could just copy this one from Canvas and put it into the strychnine folder in Topspin. That is another possibility that I think should work.
Okay, I will try that. Thank you.
Sure thing.